between the protolunar disk and the Earth's atmosphere. Take it away, Steve.
Okay, great. Can you hear me?
Yes, we can.
Great, thanks. So I wanted to talk about some work that Jeff Taylor and I have been doing regarding the mixing of isotopes and the loss of volatiles from the protolunar disk. So assuming that the moon formed following a giant impact, it would form a structure like this with a magma disk and a vapor atmosphere, or perhaps these are well mixed. We're not quite sure. The state of the liquid versus the gas, it may take time to settle into a disk. But anyway, you have this structure. And we want to understand the loss and mixing through this structure, because right now there's almost a crisis in the giant impact model. Most dynamical studies show that you should only derive something like maybe 20% or maybe a little more of the structure of this disk should come from the proto-Earth, with most of the mass coming from the impactor. And that is inconsistent with some of the new isotopic results, so it's provoked a number of models that have explored more extreme dynamical situations so that you could derive maybe 90% of the disk material from the proto-Earth, Stewart and by Cannon. And that crisis was provoked by these isotopic ratios that have been measured in the moon, and these are supposed to represent bulk abundances within the moon, and this is a very large list. Many of these isotopes reveal that the moon is indistinguishable from the Earth isotopically, with the exception of just a few. The hydrogen, nitrogen, and zinc appear to be different. It's easier to see this trend on a plot of the isotopic fractionation of these different species on the vertical axis here. And what we've done here is plotted them versus the condensation temperature, and that's just, of course, the solar nebula condensation temperature may or may not apply to the protolunar disk, but it does show you the trend that refractory elements appear to be identical to the Earth, and the volatile elements appear to be fractionated with respect to the Earth. And this is supposed to represent bulk abundances of the moon. So this is a little bit of a confusing thing. How do you explain these trends? Why is it that the refractory isotopes are so similar, and yet the volatile ones are not? And you know, the question is, did they mix very well or not? Did the protolunar disk mix very well with the Earth's atmosphere after it formed or not? The zinc and the hydrogen isotopes would argue that they did not mix too thoroughly. And the fact that the moon is depleted in volatiles like water argues again that it's not simply Earth mantle material. So there was some separation of these two things, and they were not well mixed. And yet, the oxygen isotopes especially are very constraining, that these would argue that you do have to mix the materials very well, because Olivan and Stevenson showed that for the likely difference in oxygen isotopes between the Earth and the impactor, you would have to derive the moon from over 97% Earth material to get such a small difference in oxygen isotopes. And that is why we have the motivation for saying that maybe that dynamically it was mostly Earth material, but still 97%. That's a lot of material to come from the Earth and very little to come from the impactor. So what is the deal with mixing? That's what we're trying to understand. Now, Olivan and Stevenson argued that there should be effective mixing after the protolunar disk forms, because the interface between the disk and the Earth's atmosphere is going to be unstable. The Earth is rotating maybe every 5 hours, but it's rotating at a rate that is much slower than the orbital velocity of this disk. So at that interface between them, there's a velocity shear. And that velocity shear between the two components ought to lead to instabilities like Kelvin-Helmholtz instabilities. And these should mix the material very well. And Olivan and Stevenson argued that it would. We've been investigating this, and there was a pair of LPSC abstracts. We published one in 2011 on the volatile loss, and this is from 2013 on the mixing between the two components. What I did here is I used the new set of equations. There won't be a quiz later. But we new set of equations that Ward derived to explain the vertical structure of the disk. And these are the normal hydrodynamic equations, but they allow for two phases, a liquid and a vapor, and it's assumed that they're in chemical equilibrium with each other, and that changes the sound speed and the relationship between pressure and density. And he derived these to explain the vertical structure of the disk, but we applied them to the vertical structure of the Earth's atmosphere to ask the first question, where is that interface between them? And so integrating those equations, we could come up with relationships for the density and other quantities as a function of distance from the Earth. So what we did here is I've assumed that the rotation of the Earth's atmosphere is the same as the Earth's rotation, something like every 5 hours. The disk has a Keplerian rotation here. We've assumed some parameters like 8,000 Kelvin at the base of the Earth's atmosphere following the impact and a 20% vapor fraction. And integrated those equations to find how the density varies as a function of distance, and it drops off precipitously. There's effectively a scale height of 20 kilometers. But one of the interesting things is even at 1.05 Earth radii from the center of the Earth, the density of the Earth's atmosphere is still so dense that if in this subdisk here, in this magma subdisk, you had 100 micron droplets of magma droplets, they would still see such a drag force from this density that they would deorbit in the air. So this is about where you have to put the inner edge of that disk. So, and the temperature, by the way, it's lower than the 8,000 Kelvin. By the time you get out there, it's close to 2,000 Kelvin. But the fraction of material that is gas is still on the order of 20–25%. So we call it an atmosphere, but really it's 75% liquid, and that's a surprise as well. So that's what the interface looks like. And because of this velocity difference, this is angular velocity, but there's such a velocity difference over such a short length scale that the Richardson number means this is formally unstable. So there should be vigorous mixing. And so we agree with the conclusion of Polygon and Stevenson that there should be good mixing between the disk and the Earth's atmosphere. But the same mixing that will mix material is also going to mix angular momentum. And there will be viscous torques within the Earth's atmosphere, and they're going to increase the angular velocity. From a profile like this, eventually it'll increase to something like this, and that's inevitable. In fact, whatever the viscosity law is, eventually the angular velocity will have to reach this stable profile here. This is an example of a Taylor-Couette flow from hydrodynamics. And once it does reach this state, you can show formally that the system is stable, so it should only have a laminar flow, and you shouldn't expect any more turbulent mixing. When it reaches this state, by the way, the Earth's atmosphere is not that different from the state that I showed you before in terms of its temperature and its pressures, etc. It does get pushed out, though, from 1.05 Earth radii to 1.12 Earth radii. So it swells up a little, but it doesn't change the fact that it's mostly liquid material and about 2,000 Kelvin. So this says to us that you're going to have really good mixing, but it's going to eventually stop as angular momentum is mixed. And the time scale to reach that, it depends on what the actual magnitude of the viscosity is, but it's probably, my best guess is on the order of a year or so, which is still much shorter than the lifetime of the protolunar disk, which is thought to be 100 years or so. So this leads us to a scenario for how volatiles are lost and how isotopes are mixed between the two components. You have all these species, they're in the liquid phase, and they're easily mixed between the Earth and the Moon, and that will mix the isotopes very effectively. The amount of mass that can be moved is quite large, but then eventually this is self-limiting, and so then you have a separate system now after it's been well mixed. And as cooling progresses and as the liquid fraction increases and the droplets sink to this magma subdisk and you're left only with a gaseous atmosphere on the order of 10 to 100 years, then you'll end up with a situation where all the refractory elements remain in the magma phase, but only the most volatile ones can persist in the atmosphere. And we showed in 2011 that when the molecular weight of the atmosphere reaches low enough values, basically when there's mostly water in the atmosphere, then you can have hydrodynamic escape, which is the only type of escape that can change the volatile composition on short time scales that you need. And during this stage, this is when you lose volatiles. This is when you can lose things in the atmosphere like zinc. And this is when you might get isotopic fractionation. Hydrodynamic escape doesn't directly fractionate the isotopes, but there could be isotopic fractionation during partitioning of water between droplets. And the isotopes in the vapor light. Okay, I'm almost done. And so you can get some isotopic fractionation in this stage. A quick estimate tells us that it's possible to get a bulk D to H ratio in this phase comparable to what is observed in the moon, if you lose about 98% of the water. So a bunch of conclusions, but basically we think that mixing is effective, but it's self-limiting, and then after the isotopes mix, you have a disk that is separate from the Earth. Then you lose, through hydrodynamic escape, anything that's in the atmosphere, and if the things in the atmosphere have been isotopically fractionated during partitioning, then you can change the bulk abundances of those isotopes, which probably explains why the volatiles and the volatiles alone seem isotopically different. All right, thank you.
Thank you, Steve. It seems like we've got multiple attendees typing. We'll give them just a second to get their questions in. Okay, so we've got a question from Romaine. How can it be explained? How can the DH signatures, similar to the terrestrial signatures in the melt inclusions in pyroclastic glasses or in apatite in some samples, if the D and H have been fractionated before the moon formed?
Right. So I think the question is, what is the degree to which the delta D of the moon is elevated above the Earth? You know, and this is something Jeff Taylor should answer for me, but my impression is that there is a fractionation in the bulk moon. To the extent that there is, you require a process, as I showed. But it's important to note, it's not necessarily going to be the case that you fractionate isotopes in the protolunar disk. There's two steps. They first have to be in the atmosphere to be lost during hydrodynamic escape. And also, there needs to be some sort of isotopic fractionation as these species partition between the vapor and liquid phases. So if both of those conditions are true, then you have isotopic fractionation.
Okay, we've got a question from Mark Hirschman. Does it matter if the gas left in the disk is chiefly H2 rather than H2O? One might think that the H2O is too oxidized to equilibrate with the protomoon.
Yeah, it's a good question. What is the state of hydrogen? You know, the nice models by Shannon Vischer don't include hydrogen, so I can't say what is the state. But look, if it's in H2, it's going to fractionate more easily.
Yang Liu has a comment for the magmasphere disk containing the droplets. I think one factor may be important is the size of the liquid droplets and surface area. She would like your thoughts on the surface area size effect.
Right. So the mixing, anyway, between the magma disk and the atmosphere of the